Hi everyone. Today let's discuss basic exponential functions. You see in the images before you on the left hand side is a list of 7 basic rules of exponents that you should review. You would have had these in algebra, but since we're going to be dealing with exponential functions, those are important for you to review. Also a reminder that the number e, that we will discuss the derivation of e later in the course, but that the number e is approximately 2.71828, etc., with a non-repeating, non-terminating decimal expansion. Okay, and then some basic exponential curves in the two figures before you that I would like to briefly discuss, and then we'll add on to that basis. Notice in the image y equals 2 to the x power. If I substitute in x equals 0, your rule of exponents over here says a base to the 0 power, as long as the base itself isn't 0, is the value of 1. So all of these curves go through the ordered pair 0, 1. The base of an exponential curve is the number that you are exponentiating. Okay, and so at each of these cases, both the figure on the left and the figure on the right, they're basically, you're looking at curves of this type of form. Y equals a to the x, where a is the base. And typically, when we consider the base of an exponential function, you'll notice that the base in each of these scenarios is positive, because we get some rather interesting and odd-looking functions if the base were negative. So across the board, we're only looking at exponential functions where the base is positive. Now let's take a little more detailed look at these three curves. First of all, these guys are increasing from left to right, so these are called or referred to as exponential growth curves. Secondly, you'll notice from the previous picture that these guys decrease from left to right. These are called exponential decay curves. And as you can notice, it does have to do with the size of the base determining whether you are growth or decay. So if you're exponential growth and your exponent's positive, your base is bigger than 1. If you're exponential decay, and that means that your base is positive, but it also means that your base is smaller than 1. Of course, predicated upon the fact that you're dealing with just x in the exponent. We'll talk about that more a little bit later. Okay, I do want you to notice that if I graph 2 to the x in red, if I come over and in green reflect 2 to the x, which goes through the point 1, 2, 0, 1, 1, negative 1, 1/2, it would now go, if I reflect it across the y-axis, it would go through negative 1, 2, 0, 1, 1, 1/2. This guy went through 2, 4 here, so its companion over here would go through negative 2, 4. And when I draw this guy, he's an exponential decay curve. Whoa. Okay, so let me straighten that out. When we note that what I did was reflected, sorry for the messy graph, reflected the exponential growth curve, 2 to the x, about the y-axis. In our graphing technique world, that means every x is replaced with negative x. However, that is exactly the same graph that we have over here and referred to as y equals 1/2 to the x. So why is that? Well, I want you to notice with rules of exponents, 2 to the negative x is the same as 2 to the minus 1 all raised to the x is the same as 1/2 to the x. Okay, so this guy and this guy are the same curve. Okay, and that's what I meant about if your exponent's positive, then if your base is bigger than 1, your growth. If your base is smaller than 1, your decay. It's the other way around if your exponent is negative, such as this one. Okay, but please note the consistency here with the rule of exponents. Okay, so basically for every growth curve you have, notice right here, there's a decay curve that you get by reflecting about the y-axis, and then furthermore 1/3 to the x could have been written as 3 to the negative x power. Okay, now something all of these curves have in common is the fact that their domain values, whether your growth or decay, is a set of all reals for each, and the range values for each is the set of all positive y values, so 0 to infinity. And the idea here is the following. There is a horizontal asymptote, y equals 0, because if you take a non-zero number and you continue to exponentiate, whether I'm using the figure to the left or the figure to the right and using those formulas, I would never actually get to the value y equals 0. Now, once you can separate in your mind growth from decay and how they're related by y-axis reflections, then you can move on and ask yourself, what about shifting, stretching, and reflecting? And certainly any techniques that we've already used would come into play. So here, for example, if your original graph is y equals 3 to the x, how would you graph y equals negative 3 raised to the x plus 2 exponent? Now notice, the base is not negative. That's negative 1 times 3 raised to the x plus 2 exponent, and then finally minus 1. In our graphing technique world, that is following the pattern of work your way inside out. First, this guy would be left 2 units. Secondly, you would deal with an x-axis reflection. And lastly, you would deal with a shift down 1 unit. Now let's see how this looks. Okay, so if I were to track this guy, and I'll do it in a purple color here, and if I were to go left 2, then this point 0, 1 would be at negative 2, 0. When I reflect across the x-axis, negative 2, 1 becomes negative 2, negative 1. And then furthermore, when I shift upward 1 unit or downward 1 unit, it's going to move that. So if I go down 1 unit, you land here. Okay, so we went here to here and finally to here. Since your original asymptote was y equals 0, when you move left or right, the asymptote didn't change. And actually, let me insert this in here. When we reflected, the asymptote didn't change. Okay, but when we did shift vertically down, it did change. So you can follow the vertical shift and determine the equation of the new asymptote. Okay, all right, so to finalize this, the domain of the final graph is still all reals, but its range, because we have moved it around, is now negative infinity all the way up to negative 1 and not included. and more on this topic in subsequent videos.